Alright. I think we got levels. We're good. We're streaming. We're live. Hello. Welcome back. I am Agent Ultra. And on this stream, I, program whatever. We make stuff. But we do it mostly, usually often, in the Haskell programming language. This week and for the past few weeks, we've been working on a project to implement and learn about how to implement, actually, wave function collapse. It's a procedural generation algorithm used to generate big textures of things for all kinds of stuff in game development, and you can use it for all kinds of other things too, generating poetry and whatnot. And whatever. So basically the idea is you want to start with a little bit of data and make bigger data that looks kind of similar to the input data as the general gist of things. We've been working a lot on the pre-processing part of this algorithm. This algorithm takes a few steps of pre-processing in order to do. But yeah, you start with like a little image like this, and you can generate big ones like this one, or that one, or whatever. And you can use it for all sorts of things. And so we're trying to learn how to do this in Haskell, and learn about the algorithm and all that sort of stuff. So yeah, let's get started, shall we? I'm gonna fire up my editor and all that jazz and stuff. The code for this is all on GitHub, as usual. I will try and post the link to it at some point, and all of that as well. And of course, as I'm going along, if you ever want to ask a question about what I'm doing, or what have you, just let me know. I'm happy to take diversions, backseat programming, all good. We're doing this together. That's what it's all about. Green juice is back this week, so cheers. Let's go. Open up our code. Oh, I didn't push those up, so let's push those up. Okay. There you go, let's make that fit. And I'll post a little link here in the chat to this really handy blog post about how to implement it. I find like the original wave function collapse algorithm GitHub is like okay, but not the greatest to actually learn how to implement it and how it works. This is very good at explaining quite a bit about it. So this week we finished off the frequency hints. We have kind of a basic implementation of that. And now we got the adjacency rules to tackle. And see where we go. Let's see where we end up tonight with that. Okay, let's see. Source, algorithm, wave function collapse. Here we are. Alright, there's our handy dandy frequency hints. Not the most efficient algorithm you've ever seen, but yeah, it works. We're not expecting huge amounts of patterns for most part on the input images, which is what this is generating from, so should be all good there. So the frequency hints generates a map of how many times a particular pattern was seen in the pattern input set. Like a histogram almost. That sort of thing. Including itself. So that will always be at least one. We fire up the builder. Sorry, my throat's a little dry today, so I'm drinking my juice here. We're going to stack. We're going to use our test runner as the builder, just so we can get those going all the time. We use file watch. And boom. Cool. I was thinking of another property test at some point we might be able to add here. So we're going to be working on adjacency rules. I'll get to the property thing when it comes up. The core will produce a grid of tile indices where each index corresponds to a single pixel in the output image. The core will produce a grid of tile indices where each index corresponds to a single... Okay. So our output image, I guess we can think of like a grid where each cell in that grid is going to have tile indices in it. For a given tile index in a cell of this grid, the output pixel corresponding to the cell will be given the color of the tile corresponding to the tile index. Only the color of the top left pixel of the tile, or in our case pattern, we call it patterns, will be used. Keep in mind, for this section, for every pattern placed, only a single pixel of the tile, its top left pixel, is actually added to the output image. As the core assigns pixel indices to grid cells, we can say the core assigns the top left corners of the tiles to the output image pixels. Remember that the goal of the image processor is to produce an output image where every tile-sized square of pixels occurs in the input image. All right, so this is like when people describe this algorithm, they talk about self-similarity of the output. So the idea, I guess, is if you take if you generated this with an n by n squares, like usually 3 by 3, say, and you go into your output image and you cut out any 3 by 3 square, you should be able to find that square in our set of patterns that we cut out, right, from the input image. So in order to meet this goal, we must ensure that whenever the core assigns the top left pixel of a tile to a pixel of the output image, the rest of the pixels of the tile map end up in the right places as well. This is best explained with an example. Here's a zoomed in section of the banner. This is what tripped me up the most when I was first reading about the implementation from, say, the wave function collapse README. I assumed that you would take the patterns of the tiles and you would like stamp them into the output image somehow, right? And you would try to line up or overlap parts of it with the other ones based on how you cut them out or something like that. But it's only the top left pixel. And yet the algorithm still generates these images that are supposed to look self-similar. If you're only using the top left pixel of all of these little patterns that we've cut out, how does that work? And this explains it pretty interestingly. So there's the zoomed in part. We've got a red square and a blue square. These are two overlapping patterns cut out from the input image, right? So the 3 by 3 pixel square at the red border, it occurs in the input image, rotated anti-clockwise 90 degrees. So rotated the other way, 90 degrees. Below the bottom right flower. Let's assume it gets tile index 7. The core algorithm decided that the grid cell corresponding to the top left pixel in the red square should contain tile index 7. So the core algorithm decided the grid cell corresponding to the top left pixel, I guess this one here, where my mouse is right here, should contain tile index 7. Even though tile index 7 refers to the whole 3 by 3 tile, but only the image processor knows this. Choosing tile index 7 for this cell resulted in only the top left pixel of the output image being populated. But somehow the rest of the red square ended up looking like the tile with tile index 7 as well. Why? This is the great question. So every time a tile index is assigned to a cell, we want a way to make sure that the entire tile's pixels, not just its top left pixel, end up in the right output pixels, relative to the tile's placement. Since each tile placement just contributes the tile's top left pixel, or pattern, top left pixel, we need to make sure that whenever a pattern is placed within the tile size pixels of an already placed tile's top left pixel, that's a tongue twister, that the newly placed pattern's pixels don't conflict with the pixels of the already placed pattern. Okay. I don't know if you can visualize this in your brain. It's kind of hard. I'm having a hard time thinking about it, but a convenient fiction to help us picture this is to imagine that whenever the core places a tile in a cell, each pixel in the tile size square of pixels, whose top left corner is that cell, is colored to match the corresponding pixel of the tile, but only only the top left is marked as populated. Unpopulated but possibly colored cells can have tiles placed in them as long as all cells in the square filled by the new tile are not yet colored or contain the same color as the corresponding pixel of the new tile. So what I think ends up happening is, because of the way we cut out these patterns from the input texture, and because they overlap, right, shifted only one pixel at a time, so there's a lot of overlap between each of them. And with the adjacency rules we're about to generate, even though the output image, we only take that top left pixel and populate that, the other tiles that are allowed in the adjacent cells, right around here, are also going to have, like, their top left is going to be a green pixel, right? And this one over here has to be a blue pixel, because it has to match everything that's in the red, but we only have to actually place the top left one. Hopefully this will become a little bit clearer as we go along. So let's generate the adjacency rules to force the core to never place two tiles in positions where their overlapping pixels conflict. This is the secret sauce. Or not so secret sauce, but maybe it is the secret sauce. Recall that an adjacency rule is the form. Tile index A may appear in the cell 1 space in direction from a cell containing tile index B. The rules should only permit A to be placed adjacent to B in direction if doing so would not cause a conflict. All non-conflicting adjacencies should be allowed. Alright, so we have some example code here for how they generated in their algorithm, I guess. The compatible function returns true if and only if overlapping with A with B. If B is offset by one pixel in a direction, the overlapping parts of the two tiles are identical. Okay, so we're going to have to implement compatible. Sounds like. And I guess we'll need a mapping here. Some kind of structure here for the adjacency rules themselves. And because we could also include the rotations as well. Maybe the rotations might also overlap as well. In fact, we might already have implemented this, actually, with overlaps. I believe that's a binary Boolean valued function there. Yeah. That's our overlaps, or in their case, they called it compatible. Cool. Okay, so we've already got that part. That's good. And yeah, so in the example below, A, B, right is true. Right? So this part of B overlaps this part of A. All right, so now, once we've picked that top left pixel of A somewhere in our output grid, right, the adjacent pixels, because of the way the wave function will collapse the adjacent pixel, right, it's only going to pick on the right-hand side, in that direction, right, in our map, the adjacency rules that of the tiles that are allowed to overlap. Right, so it'll pick B. B will be at least one of the available ones. And then that might be the one that we need to collapse next, so we pick the little top left corner of that one, and so on and so forth. And because they all overlap, it kind of collapses all together and creates the output image this way. All right, in this example, they're 3x3. The adjacency rules only ensure the adjacency rules are compatible. It is possible for a pair of tiles which are 2 pixels apart to overlap. What prevents them from conflicting, though? Consider this example. We got 3 overlapping squares here. Red, blue, and black. They're all offset to the right by 1 pixel each. So the red and blue squares surround the tile placements which are 2 pixels apart. Right, this little strip here in the middle. They aren't adjacent, so the adjacency rules don't explicitly forbid the red tile's pixels and blue tile's pixels from being different in the intersecting area. However, the existence of a black square, which is adjacent to both the red and blue squares, means that the red and blue tile placements won't conflict. Right? And that's why all these overlap, like overlapping cards. Right? If you imagine the patterns like that. Because they're adjacent, yeah, and all that stuff, they won't conflict, basically. That's pretty cool. All right. Okay, so what's our structure, our adjacency map structure going to look like? All right, we're going to have, well, let's define that. Adjacency rules. Like allow A, B direction is what they did. So it's kind of like a lookup map, because I guess in later steps we're going to want to also look at the adjacency rules to see, is this allowed? And I'm going to give you 2 tiles in a direction, and you're just going to return a Boolean. Right? Probably something like that. So we can make it like a new type wrapper over a map, I suppose, where the key is that triplet pair of tile indices, and 2 tile indices and a direction. New type, adjacency rules. And this will be function to get them out. It'd be our map. We said it was going to be a index, and direction. And we're going to return a bool and restore a boolean there. Although it's not like int, really, it's index. We can probably just use a type alias for that, just to make it a little bit clearer. And yeah, tuples can be kind of useful, but I prefer records. I wonder if we could actually use a record there, and that way it's kind of a little bit more clear what part is what. Let's see. Actually, I haven't tried that before. Let's give it a shot. What do we want to call it? Like tile key? Adjacency key? I'll call it tile A, tile B, direction, or patterning, I should say, just to be consistent with our naming. And dir direction. Might need like some sort of hashable thing, maybe. Deriving. Go. And let's pop it in here. Just fine. Okay. So those are adjacency rules. Boom. So So we want to have a function called allow. And we're going to take I might still want that tile index. New type. Or type alias. Take a tile index, and a tile index, and a direction. All allow is really going to do is just insert into the map, really, into our adjacency rules. Adjacency rules. That's the thing we're changing, and then we return a new one. Tile pattern index. Yeah, I could probably do it there as well. Why not? Okay, pattern index, there we go. Pattern A. Allow A, PA, PB, direction, DIR. And we will use map. I think we'll use update. And it's like that at that. Let's see. We have map and scope. Yep. Key. We'll just construct the adjacency key here with D of A, D of B, and DIR. And true as the value to set. Probably not the right type, maybe. I gotta fix this. What the heck? It's annoying me. Later, list a filter, check source. I just like not expand it properly. Could I shrink it? That jumps. That's over. Okay. What did I do? Check expand error list. Fly check is the error checking mode I'm using in Emacs here. That's pretty common. I'm not obviously clearly not a super user here, but it's been like this for a while now. I don't know what I did. Clear error thresholds, error highlights, error levels. Like it's working. But it's just not showing the whole thing. Jump to next, jump to previous, explain, filter the error list by level, and then filter. Sort. Apply check list errors. Lane. No, that was not it. Lane. Okay, you don't want to. Now we lost it all. Okay. We're gonna restart the editor. I don't know what I did. I did something. I just want my full errors back so I don't have to look. Layering buffer. And the errors list. I don't know. We might just have to live with it still until I fix it. We'll fix it another time. Anyway, back to what we were doing here. It clearly wasn't a quick little thing. Okay, so what do we got? We got adjacency key, too many arguments. One, two, three arguments to me. Looks 1, 2, 3 there. That's weird. What's the other one? Ah, yes. So adjacency rules. In order to do the map update, we gotta unwrap the adjacency rules. We're gonna get the adjacency rules. And then once we do the map update, we wrap that back up in our new type. And update. I just got the arguments wrong on that one. Haskell, map, okay. Update. Okay, it takes an A. Oh, okay, function A maybe A. Okay. We want not quite update. What is it? What else is there? There's a bunch of them. Insert. Yeah, insert should be good enough. What we want. Yeah, because there should only be one rule. And if we allow a new rule in the future, just overwrite what was there. Insert. That is key value in map. Okay, so we do need ORed at least to be a key, which is easy to derive, that's no problem. And we need ORed for direction as well. Also, not a problem. Success, it compiles. Okay, so allow, and what else do we need? We need a we need a query. Allowed. And for this one, we'll take the adjacency key. Oh no, we can just maybe just do pattern index. Pattern index. A direction. Some adjacency rules. And a boolean. That's really just the lookup. And I guess that'll be a maybe bool, because it might not exist in the map of adjacency rules. So, first things first, we gotta get adjacency rules. And then we can do our map lookup. And we'll do adjacency key. PA, PB, BIR. If I could spell adjacency is such a weird word that I don't spell very often. It's sticking out of my brain here. Okay, no problem. No sweat. I mean, we could write some tests for this, but I mean, they're not going to be terribly interesting for now, unless we decide to change the implementation somehow. Maybe we could. Just for posterity. Quick little one. Ask spec. So we're going to describe. Adjacency rules. We're going to describe... We're going to have a property. We'll do it as a property. Generate those tests. Allowed rules are always allowed. Allowing allows is allowed. I don't know. Always allowed. Trivial one. For some pattern index X and Y. And we might have to come up with arbitrary index for, or arbitrary instance for direction. Such that if we allow X, Y, and D in this will need some base empty map. Adjacency rules. Or empty rule adjacency rules. And then that should be allow followed by allowed. I think this one will have to be in parentheses. That should be in scope. Update empty. Pattern index, direction, adjacency rules. Oh, should be just true. No. Okay. No problem. So empty adjacency rules. Pretty easy to implement. Adjacency rules where we have map.md. Good. All right. That's that part. And then put a building. Let's test. Boop. Allow. Oh, yeah. Oh, you have to pass the adjacency rules. Yeah. Pass a D and then rules. Yep, so that's the... So, for direction... where arbitrary equals one of up, right, prime, down, left, prime. Just one of, like all lowercase. Here. One of takes a list of generators, so we're just going to just return a thing. Okay, always allowed is allowed. That's a pretty trivial rule, but we'll probably find a pretty trivial little property, but we'll probably find some ones. Maybe we'll find some ones out after we get to the next step. So the next part is generating the adjacency rules from our list of input patterns that we've cut out. Generate adjacency rules, and we'll give a list of pattern of A as our input, and then we should get adjacency rules as output. This. Okay. All right, so just like the algorithm shown in thing, we have to iterate over the patterns, like for all the pairs in the patterns, and then for all the directions, we check if they overlap. And if they do, then we add them using allow. So, pairs of the list. I think there is a function like that already. Tall graph, consecutive pairs. Sort of like the permutation of sets of size 2. Oh, I've probably written that before. It's combinations. Permutations? Oh, there's one in list. Okay, cool. So we take all the permutations of patterns, limited to the ones that are size 2. We should. Starting with the empty adjacency rules. Over. After we first take the filter that and permutations of the patterns. We want to take where the greater than or equal to after taking the length. And do this. Let's take the list, the permutations of the list. Let me just double check that that actually means what I think it means. Do I have it in scope? Let's just add it. We'll take permutations of this list. 1, 2, 3, 4. All right, they're going to be all same length. Okay, that's not going to work. What do I want? I want like combinations. Or what if I just took the first 2 elements of each of these? No, I'd have duplicates because I get 2, 1 here, 2, 1 here. Yeah, we don't have to be super clever. We could just do nested lists. Take patterns. Right, we could do No. Take, so let's screen X, we'll go equal 1, 2, 3, 4, 5, like this, and tails of X. I get this, it's slightly decreasing. There we go, 1, 2, 3, 4, 5, then we get 2, 3, 4, 5, then we get 3, 4, 5, and 4, 5, and 5. We want to that map with that maybe. A and a list of B's. And then some list of A's. Then we get a list of B's. And take the zip of X and tails of X. Too few. Zip X with the tails of X's. You get 1, 1, 2, 3, 4, 5, whatever. 2, 2, 3, 4, 3, 3, 4. No, it's not quite right. Let's just Google it. Combinations size 2. That's a pretty concise looking one. Put X there. Oh, ends. Got 2 of X. 1, 2, 1, 3. 2, 1, 4. 1, 5, and then we got 2, 3, 2, 4, 2, 5, 3, 4, 3, 5, and 4, 5. Now it's almost quite, because I need 1 paired with, I need 1, 2, 1, 3, 1, 4, 1, 5. We've got that. Then I need 2, 1, 2, 3, 2, 4, 2, 5. Okay. That's what that code's doing. Alright, so we got A is 1, we get... Well, then we got 1, 1. Well, that's kind of awkward. And then we get 2, and then 1, 2, 3, 4. Yeah, so... That's kind of what we're going for. We'll take zip X with Cycle of X. What do you got? 1, 1, 1, 2. Same as the other thing I was doing. Kind of like that, only bundling it together. Probably just a little bit. What else can we do? Well, we can do... Oh, we could do all of the indices in the range here as at least... Yeah, let's... If I did it as list comprehension, we'll generate the pairs that we want from X and Y. Where X will be 0 to length of patterns. Y would also be that. Right, we'll do X, Y like this, right? I think we've done this before in the space game a fair bit. Say 0 to length 5. Y will get the same value, same range of values. 5. 0, 0, 1, 0, 2, 0, 3, 0, 4, 0, 5, 1, 0, 1, 0. All the way up. Okay. 5 is inclusive. Just minus 1 off of that. So there's our indices, our pairs of indices, and now we should be able to we'll need to actually get the patterns out to do overlaps in order to build our adjacency map here. We'll do the fold L, the old fold L prime. We have some function, we'll have the empty adjacency map here. And over our pattern indices is what we will iterate. Our empty adjacency rules. Say, oh god. We'll call it add rule. Here. The old undefined trick. Yeah, so the type of this is going to be the adjacency rules. Pair of indices. A pattern index. And we have to return adjacency rules. All right, so that's the one we're accumulating into, and then we're going to return a new one there. Pattern A, pattern B. Okay, so then we have to get those out of the patterns here. If we implement this properly, all the indices will be safe. I'm going to use at this level, like we shouldn't encounter any problems, using the list indexing operator to get those out. I'll call it A index, AX, and BX. Pattern A. Patterns. Stop bang. AX. And pattern B. Patterns. Grab T. And stop bang. BX. Okay, and so we have two cases. If overlaps, pattern A, well, then we have to do the directions. Let's fold over that directions. And we'll fold over the accumulator as our starting point. Yeah, over the directions. Up, right prime. Down, left prime. And add rule 4. And this one's going to be maybe not like this, just like this. Maybe just like that. Let's stop bang bang. Yep, cuckoo. Let's stop bang bang. So we want it's going to be adjacency rules, direction, and we're going to want to add rule 4 to have actually a couple more parameters. We're going to want it the pattern A, pattern B for each direction. Adjacency rules. And I'm just going to bring that over a little bit so it's a little bit more readable. Type's getting loud. Okay, so the R's we're going to accumulate into pattern A, pattern B, direction D. Adjacency rules. So now we can add a rule. If it's allowed. So we can add a guard. Right. Such that overlaps pattern A with pattern B in direction. Then we will allow ooh. No, we'll have to move this down. This will be AIX, A index, B index, and these will be pattern index. We can call it BX again. Okay. In which case, we can't use the guard. But we can just use, we can use that to get those out again. If overlaps, pattern A, pattern B, in direction D, then something else. We just return the accumulator as untouched. We have to modify the accumulator here. We just allow AIX, BIX, D to R's prime. Yeah, that's the problem here. I just have to move this. Oh, yeah, because I put the AIX and BIX first. Yeah, so I just have to move adjacency rules down. And then move this over. Okay, and then overlaps is a problem, and that is pattern A direction should be fine. What is the problem? Equal A, eq A. I just need to add ek up here. Yeah. I think we're all good there. Yeah. Okay. So we generate our adjacency rules. What can we say about this so that we know we've implemented it properly? Well, if there are no patterns, obviously we're going to get the empty adjacency rules. That's pretty trivial. There's going to be some number of adjacency rules generated from a particular set of patterns. What would that be? So if we ignore the set of like rotated patterns, we know that in say a 10 by 10 input image, input texture, there's going to be 100 patterns generated. And there's 4 directions. And we know that they all overlap. Most of them overlap with each other. In the 3x3 case, we're going to get, let's see, 3, 1, 2, and then 1, 2, and down, 1, 2 to the right, and 1, 2 to the top. 2 in each direction. It's 2 to 4. It's gonna be like, sorry, 8 times 4. That's gonna be 24 overlapping patterns for each pattern. Patterns. So that'd be 2,400. There should be 2,400 entries, maybe. Let's see if that's true. Number. So we'll take an arbitrary texture in this case. And we'll get the patterns out of it using our patterns function. Where is it? Over there, yeah. Patterns of texture, size 3. We're going to have to state this more generally. We're not generating a texture of 100. But we know the fixed number of 3 of n. So if we take these patterns, we put it into, we generate our adjacency map, our adjacency rules. Four P's. And we could say, oh, we need to query the number of rules. Okay, and we could say that the map, you have like a number of members function query. Size, number of elements in the map. So we map dot size after taking get adjacency rules of generated rules. Now we need to express this as a formula because we're taking an arbitrary texture. So the number of patterns, I think, might play a part in it. And the size, maybe the size of the texture itself. So the number, in a 3x3 case, I guess the number of overlapping textures we'd expect for any texture in the set would be the square of 3 minus 1, or square of 2 in this case. 3 minus 1 squared. And squared again. So if we took 4x4, would that make sense still? Maybe 3 on each side. Maybe 6. No. Maybe 6 and 12. So the number of sides is n. N minus 1 times 4, I think is probably it. Okay, so it'd be 2, in the 3x3 case, it'd be 2 on the top, 2 on the bottom, that's 4, 2 on the left, 2 on the right, that's 4, 4 and 4 is 8. And if we did 4, 3 per side, it's 12. Yeah. Makes sense. Okay, so we know how many overlapping tiles there are for the size of n. In this case, in this test case, it's fixed 3. So that's times the number of patterns there are in total. Could be the number of overlapping things. So since we got a constant, we'll take the length of patterns times uh, 8. I meant hex. What do we say here? All right, like the piece. Okay. So is our test right or wrong? I'm just going to look at the generator for texture again quickly. Okay, so X's. List. This our size. Getting somebody from X's. Okay, so X is just an infinite list of whatevers. In this case, all zeros. Okay, so the values don't really matter so much, I guess. So we expected, in this case, 648. We've got 26,244. So, right off the bat, we're doing we're doing, oh wait, let's make sure that patterns isn't also including the rotated ones. I think we took that out. Yeah, we took that out. So it's just the extracted patterns. Okay, cool. Alright, so this list here should be the list of X's and Y's. So this should be in size of the length of patterns by length of patterns. I take length of this 36 elements for 0 to 5, 0 to 5. This one, so I should take the 5, so there's one. This one. 25. 5 by 5 squared. This should be 7 by 7 squared. 48. 49. And for each of those, add the rule for each direction. Now, in this case, this array here, this texture, it's all zeros, so everything should always overlap in every direction, no matter what. Every pattern should overlap in every direction. So it would be for each pattern, and every other pattern, in every direction. And maybe that's right. We're too restrictive here. It would be something for not this piece. Yeah, we got a failure. Yeah, we're expecting way too much now. Alright, so we took the length of the piece. That. But we also have to factor in the number of directions. Close. I think our implementation might be right. Or we just can't formulate it this way. Because arbitrary texture, well, there should be some number of overlaps there. What is the number? Fun. Well, is there other different way we can explain it? The other thing I was thinking, like before earlier, at the very, very early beginning of the stream, was a similar kind of property test, but just taking the first 3 patterns in a 3x3 size, and they should all overlap in a particular direction. Like we're saying in the image here on the blog post. Right, if this was some pattern, the next 2 patterns to its right. Right, this black one should overlap with it. On the one after, well, I guess by pair, if you go by pairs, right, they should all overlap to the right. At least in that row. I will put it there. Let's just clean this up and commit this and move on. I think that's good enough. If we can come up with a better property, we should definitely add it. Because the whole purpose of this, doing this with like pure data structures or with immutable data structures at first, because I know I'm very certain it's going to be inefficient when we get to the algorithm proper. is just make it as correct as possible. And when you're talking about correctness of computer programs, for example, you really have to ask yourself, correct with respect to what? And in order, the what we need to be correct with respect to is generally some kind of specification. I want to say that it should, what our software does, and probably more importantly, what it doesn't do. And the bounds that it kind of works within, so that we know that if we've written the code properly, it implements that specification. Right? It's correct with respect to that specification. Which is easier to do with pure code. First, in Haskell at least, I find. And just probably in general. You know, every language, I imagine. And then we can move on to the mutable stuff. We want to actually like make it fast. Work with really big textures. And then we have like a test oracle. We have an implementation we know that is correct with respect to our specifications, and then we just have to test that our mutable one follows the same specifications as the pure one. And so anything the pure one generates, the mutable one should generate too. Well, I mean, at least behave the same way. Okay. So I don't know if this is a deterministic algorithm, actually. I think the idea is that you can generate from one image many different ones. So there's got to be a little bit of randomness there. Although you probably could use a seeded randomization step to make it deterministic so you can test those things. Okay, so we have our adjacency map. Cool. I think that's the processing... Our adjacency rules. I think that's our processing good and done. So after pre-processing, the frequency hits and adjacency rules will be passed to the core algorithm, and it will return a grid of tile indices. To produce the output image, we'll need to know which tile index refers to which color. To help with this, the preprocessor outputs a map from tile index to color of the top left pixel. Simple enough. Alright, so they're implementing a tile index grid like this. A grid of tile indices. And then the top left pixel of each tile is a hash map. So we can do a map as that to those as well. And regenerate that even. Pass it into this function and get an image out. We'll probably output a texture, and then it'll be up to our user to convert that into their image format of choice. And then the final step is trivial. We'll take the grid of tile indices produced by running the core algorithm on the adjacency rules and producing hits from the preprocessor. Top left the color map and return processor. Create an output image, same dimensions as the grid. For each tile index in the grid, set the corresponding pixel color to the output image. Tile index map, yeah. Color map. Cool. Alright, one more pre-processing step. And then we are ready to go. So we will generate this map here. Tile index to whatever value. We'll call it color map. We'll give it a color map. This will be a map from tile index to some Or not time, pattern index. Forgot about this. Okay. Name shadow binding. Okay, better. That was probably broken. Oops. It technically wasn't. We shadowed the name here. We unshadowed it. Hurry for us. Okay, anyways. Color map! Yay! I haven't pushed that yet, so actually I'm gonna just create commit here for that. Switch. Cuckoo. Alright, let's move data, new type color map of a color map, a map of pattern index to some A. Pop those on there if we need them. We need to make the color map. We can call it generate color map. Then we have to take a list of patterns. Okay. This will be bold. We'll start with the empty color map. We'll have to define that. And it'll be over patterns. So we can remove that. Okay, empty color map. Here's a color map. And we define it like so. Very simple. Ooh. Yep, no, this should work. Now we do that empty. Hirugi. Pattern. Alright, that's going to be a color map of A. A pattern of A, and it's not preparing a color map of A. And this will be map, insert, pattern index. We're up to zip this first with its indices. So this will be the pattern index. And a pattern A. We need that. Okay, and I'm going to pull that map here. Map and index B. And insert at p.index. The top left pixel of pattern of B into CMap. And top left of and we can destructure out a pattern here. Overload it with record wildcards, and we do something with that. So we have the get pattern. That's going to be our array. And we're going to index into that. That's 0, 0. We know that should be safe. And that should be get pattern. Yeah, get pattern. Array.bang at 0, 0. Oh, was insert not the one I wanted to get? Oh, it was, yeah. Oh, we have to return a color map. Yeah, that's right. We have to unwrap the color map first. Get color map. And then we have to wrap it back up. Yeah, we'll just line all this stuff up. Okay. So we just get all that data out to generate the color map from the list of patterns that we have here. Cool. And that should be that. Okay, cool, cool. All right. Yeah, so we can do that part later. We're kind of out of time on the stream here, unfortunately, but that's all the pre-processing looks like. So next is going to be probably the hard part, and that's where we're going to implement the constraint solver. Right. So that's going to probably involve some monads. That'll be fun. Collapsing cell, propagating state, cross things, or remaining unclapped cells, all these sorts of things. Fun times. Cool. Putting it all together, and then, I don't know. And this is the kind of thing we should be able to create. Maybe we can animate it or something in SDL. That'll be fun. Some pixel blending. So on and so forth. Alright. Let's clean up our code. And push it up and show you where all of this stuff is. I'm just going to rebase this. We're going to just squash that one up. We're going to reword this one. and that should be good. Like that. Good. And push them up. Okay, so thanks for tuning in, watching, and hanging out with me. All the code for this lives on my GitHub. I'm Agent Ultra. Been a pleasure. At wave function collapse. Boy, yeah, good times. I use all of my authentication and authorization. Thanks, GitHub, for reminding me. But there it is. GitHub, Agent Ultra / wave function collapse. I'm going to try and type it out for you so I can paste it in the chat. There we go. And there you go. Okay, so if you liked what you saw and you want to hang out with me next week as well, I do these streams once a week on Tuesday evenings at about 10 after 8 Eastern Standard Time Zone. So write that down, or if you're already on Twitch, since you're watching here, maybe you have an account, you can, follow and set up your notifications, and you'll get notified when I do go online and stream stuff. Occasionally, once in a while, I do surprise streams off schedule. And if you're on YouTube, you know what to do there as well. Like and subscribe, it all helps out. And yeah, follow the link above my head if you would like to join the Discord server, where there are other cool streamers doing programming languages like Haskell and other languages as well. Erlang, I think some other folks are doing pretty cool stuff. And follow them along there. You can there's a channel for this channel, and you can post your questions there if you didn't get to ask one on stream, or you didn't want to ask one on stream, or you just want to chat about some project you're excited about, you're working on, whatever the case may be. I'm there hanging out all the time, and I'd like to hear from you. You can follow me on socials, of course. I am on the Fediverse, on Mastodon, the TypeStop.pl server. Agent Ultra there as well, so you can follow me there. So follow me there. And then I occasionally post updates and stuff about the stream and talk about things that I'm working on, whatever. Blog posts and links to all my things are also on the profile there. And that's what I got. So thanks again for watching. I'll see you again next week. May your monads be free and your types always check. Peace out. Happy hacking and all that stuff. Stream duh.